First of all, I would like to thank the organizers for their kind invitation to this very nice place. This is the title, and this work has been done in collaboration with my former PhD student that is now in Austria at the University of Padova. Let's see. Okay, this is the summary. First, I will briefly review the BCS-BC crossover in 3D and also in 2D. Then I will show some results, theoretical results we obtained for finite temperature, but first also zero temperature. At finite temperature in 2D, to get reliable results, it's necessary to introduce vortices and anti-vortices. So I will discuss this also. As you know, as you have seen previously, about 10 years ago, the BCS-BC crossover has been observed with the ultracold gases made of two-component fermionic alkali metal atoms that can be potassium or lithium, usually. The BCS-BC crossover is obtained by changing the S-wave scattering length between atoms using a very nice technique known as Fanno-Feshbach technique. And this technique is based on the on an external magnetic field B, and changing the intensity of the magnetic field is possible to show that the scattering length between atoms changes, and can be also very large or very small, and can also change sign. For instance, here you see the scattering length on the vertical axis as a function of the magnetic field on the horizontal axis. And you see that from right to left, you see that for large magnetic field is small, let's say, and negative. Then it becomes negative, but very large, and it diverges. And then, it becomes very large and positive. And then here, it goes to 0 plus. And this corresponds to the somehow that you have to reverse the right side here corresponds to the left side here. This is the BCS regime where you have a small attraction between atoms. Then you increase the attraction. You get the unitarity regime where the scattering line diverges, and then it changes sign, becoming positive, and then you have the formation. When you have the resonance, you have formation of bound states, many bound states. You get molecules, and in the deep BC regime, these molecules are repulsive, but the repulsion is small as intensity. So, and you are going in the regime of weakly repulsive bosons. Recently, 3 years ago, also the two-dimensional BCS-BC crossover has been achieved experimentally with the lithium atoms in quasi-2D by several groups that are shown here, the papers. And what is important to say, first of all, is that in 2D, when you have attraction, you always form a bound state, and this is the binding energy, and that is related to the scattering length AS by this simple formula, this proportional to the inverse of the square of the scattering length. And if you consider the familiar fermionic single particle spectrum of BCS theory, you have the gap here and the chemical potential, and in the BCS-BC crossover, these parameters depends on the interaction. And if you are in the deep BCS regime, delta obviously is very small, and the chemical potential is practically the chemical potential of non-interacting fermions. Then when you go in between, the delta becomes around the Fermi energy of non-interacting fermions, and the chemical potential becomes 0. So at that point, you don't have anymore the Fermi surface. And in the deep BC regime, the chemical potential becomes negative, and in particular it becomes equal to the binding energy over 2, the minus. Here I have defined positive binding, and so here there is a minus. If you want to study the BCS-BC crossover, you can use several strategies. We use this one based on functional integration. We wrote the partition function Z in terms of functional integration of fermionic field psi. S means the spin, and here there is the exponential. The exponential with this S, capital S, and capital S is the Euclidean action, and the Euclidean action obviously depends on the temperature through beta that appears here. Also depends on the volume, in this case 2D volume, so in our area actually. And here there is the Lagrangian of the system, and you see there is the chemical potential mu. And there is an interaction, a constant interaction between fermions with opposite spin, and the strength of interaction is G. G is negative. And in the BCS-BC crossover, you are changing G. Unfortunately, the problem cannot be solved analytically. And okay, maybe you can perform some brute force numerics, but maybe you can try approximate analytical approaches. One way is the following. You can introduce an auxiliary complex scalar field delta, the pairing field, and you can rewrite the partition function adding an integration and functional integration over this complex field delta. And doing so, you will get an effective but still exact Lagrangian that is equivalent to the previous one that I have shown, where now there is the interaction between fermions is quadratic but is mediated by the complex field delta. So the price to pay for having quadratic terms in the fermionic fields is the inclusion of this bosonic auxiliary field. The simplest approximation is to suppose that this bosonic field is constant and delta 0. And this is the standard mean field approach. And if you apply it, you will find the mean field BCS equations. But you can try to do something better, namely to consider a constant plus some fluctuation. I call it eta. Depending on space and imaginary time, tau. Obviously, then, because eta is small, when you introduce here this expression in the Lagrangian, you stop at the quadratic term in eta. Doing so, from the partition function, exact partition function, capital Z, you will find a partition function that is the product of the mean field partition function times a fluctuation, a contribution due to these etas. And that is Gaussian fluctuation. I call it capital Z subindex G. And the ground potential, as you know, is related to the partition function by this formula. And so the ground potential can be written as a mean field ground potential plus a Gaussian ground potential. In the mean field, the partition function appears delta 0. Instead, in the Gaussian partition function, it appears obviously delta 0, but also the integration over the fluctuation etas. Well, the mean field can be done analytically, I will say, and you will get, well, still you have to do this summation, but can be done in 2D at least, and you get this formula for the mean field ground potential, and you see that the mean field ground potential indeed depends on the single particle fermionic spectrum, the familiar one of BCS theory. So there is the chemical potential, and actually there is not the pairing field depending on space and time, but there is the constant one, as it should be. There is also the contribution of fluctuations, and the Gaussian ground potential is can be written in this way, complicated, depends on this matrix M, that is the inverse propagator of Gaussian fluctuation, and the summation is over Matsubara bosonic frequencies. And this unfortunately can be solved numerically. Okay, just to give you an idea, this M is quite complicated object. Here are the two elements of this matrix, and you see this is very complicated, depends on the fermionic spectrum. So indeed, it will be the contribution due to bosonic fluctuation, but inside it there are fermionic excitations. But at least in the deep BEC regime, you can find that the fluctuation ground potential can be written in this way. That is a 0-point energy of these elementary excitation that I called collective elementary excitation, bosonic excitations, plus a finite temperature contribution. That is the familiar contribution, finite temperature of a bosonic gas, where the particles of this gas are the quasi-particles given by this energy, with this momentum, Q. And this energy is related to this frequency, omega, and omega is related to the momentum Q through this equation. That is determinant set equal to 0 of the inverse propagator M. So not easy to do. Okay, formally, as I said, you have the ground potential written as mean field plus Gaussian. Both mean field and Gaussian depends on the chemical potential, the area, the temperature, and the mean field gap. And this gap is obtained usually imposing that the derivative, the partial derivative of the mean field ground potential with respect to the gap is set to 0. So this is the mean field gap equation. Obviously, in doing so, you will get a formula that relates your gap delta 0 to the chemical potential and to the energy, and in principle also to the area or the volume. But there is another important equation, that is the number equation that gives the density. Here the density is a byproduct and obtained as the partial derivative of the ground potential with respect to mu. Notice that here you have the full ground potential, omega. Instead here you have only the mean field one. This is done usually to get a reliable theory at the Gaussian level. Okay. In 2D, as I said previously, there are always bound states for any scattering length, and the precise formula that relates the binding energy epsilon b to the 2D scattering length AS is written here, and you see is proportional to the binding energy is proportional to the inverse of the square of the scattering length, and it appears this nice number gamma, that is the Euler Mosconi constant. Moreover, you can relate the binding energy and also implicitly the scattering length to the strength G that appears in the Lagrangian, the starting Lagrangian, of the interaction between fermions. Unfortunately, this object is divergent, but there are several ways to remove divergences. One way is simple way is doing dimensional regularization, but you can also introduce cutoff, other stuff. Well, at the mean field level, the mean field ground potential, I don't know why there is, I will put it, the mean field ground potential has a very simple expression at 0 temperature. You see, the mean field ground potential is proportional to mu, the chemical potential, 1/2 the binding energy squared. And using the formula that I shown previously that gives the number equation, namely the number equation that gives the number density, you will get, inverting this formula, the chemical potential as a function of the density. And this is a very nice formula, because if the binding energy is very small, and this corresponds to the BCS regime, you will get that the chemical potential is exactly the first term. And the first term is the Fermi energy of non-interacting fermions. In the other limit, when this epsilon b is very large, the second term dominates, and you will find that mu is simply minus 1/2 of the binding energy, the other result. This is very nice, but unfortunately it's wrong. If you compare this formula with experiments, it will work only in the extremely deep BC regime, and only in the extremely deep BCS regime, but not in between. So, to do something better, theoretically, you have to add Gaussian fluctuation, but we have. And so, I include also Gaussian fluctuation. Well, if you want, I can also calculate the pressure. The pressure is simply minus the ground potential divided the volume, and you have this formula formally. And if you include this correction, the Gaussian, and okay, I skip this, and you compare, for instance, the pressure as a function of the binding energy in the BCS-BC crossover. BCS is on the left and BC on the right. You will see a very good agreement between the red dots that are experimental data obtained by this group 3 years ago, and the full line, solid line, black one, that is my theory. Well, okay, the theory of mean field plus Gaussian. If you instead you consider only mean field, the result is not so good. So it's truly important to add Gaussian fluctuation. And the agreement is extremely good. I'm very proud. This is zero temperature. By the way, at zero temperature, the Gaussian fluctuations gives this only the 0-point energy of collective excitation, this term here. But and the collective excitation are written by this formula, that is sort of Bogolyubov spectrum, where there is this lambda and this CS. This lambda is 1/4, and this CS is practically the speed of sound. And in the deep BEC regime is related to the chemical potential, to the binding energy by this formula. You can prove it. And after the regularization, dimensional regularization, the details can be found here and also in here. Well, here is my PRL of this year, where I extended these results also for a finite range interaction. You will find an analytical formula for the ground potential and immediately the pressure. And what is remarkable is that this analytical formula, taking into account Gaussian fluctuation, has a logarithm. But this formula is exactly the formula predicted many years ago by Popov for weakly interacting repulsive bosons. So, introducing Gaussian fluctuation in the BCS theory, you are able to recover in the deep BEC regime the result of Popov. This is zero temperature. Let us consider finite temperature. Okay, at finite temperature, an interesting quantity is, at least for me, is the superfluid density. And the superfluid density following Landau can be written as total density and minus normal density. But the normal density, in my approach, is written as the sum of two contributions. The normal density due to single particle fermionic excitations, and the contribution to the collective bosonic excitations. Epsilon, this capital E SP and this capital E collective. And you see here you have the fermionic contribution, because there is a plus, and here the bosonic one. Okay, but this is the bare superfluid density. And if you study this bare superfluid density, you will find that it follows this behavior. That is the typical for a 3D system, namely it goes to 0 smoothly. But you know that in 2D, the superfluid density has a jump at the finite temperature, the Berezinski-Kosterlitaulis critical temperature. And so to get a more reliable superfluid density, you have to renormalize this bare superfluid density. And how can be done? Well, you know that if you consider the pairing field we have seen previously, this pairing field has a modulus and a phase. And the phase is an angle, obviously, and the phase, and there is an angle in the phase. In the phase, there is the angle theta. And you can write down an effective Hamiltonian, that is this one, where it appears this bare stiffness, and the bare stiffness is simply related by this bare superfluid density by this formula. But as shown previously, if you consider that there could be also quantized vortices, if you want, you can. There are several ways to do, but one way is to decompose the angle and the sum of two contributions. A contribution that does not contain quantized vortices, and another computer that contains all the vortices. And after a procedure that I will show a bit, you will get that your Hamiltonian can be rewritten in this way, where now you have a different J, that is the normalized one, not bare, but obviously here you have theta 0, not theta. Okay? How to do this? Well, there is last year the Nobel Prize was given to Kosterlitz-Towles just for doing this, for having done this, and they wrote the Kosterlitz equations, and I will not show the detail. I have simply written the equations, but if you follow their paper, you will see that solving this equation, you are able to get the renormalized phase stiffness, knowing the bare one, and from the renormalized phase stiffness, obviously, we get renormalized superfluid density. Solving this equation, that can be solved also analytically, by the way. You give as initial conditions the bare superfluid density, the bare stiffness, and at the end you will get the renormalized one. Both dependent on temperature. Huh? Now I will show the plots. Okay, the dashed lines are the bare superfluid densities for different values of the interaction between fermions. You see, for instance, if let's see the yellow dashed, it goes to 0 here without jump. But instead, if you consider the renormalized one, that is the solid one, the yellow solid one, you will see that here, it jumps to 0. And obviously, the temperature is quite different. If you want, this is usually called, well, you can call it as you want, but T star, and this is T Berezinski-Kosterlitz-Towles. Okay, so in this way, you are able to get the Berezinski-Kosterlitz-Towles critical temperature. And here, there is a comparison between some experimental data that are these ugly dots with the arrow bars very large, and our theory, that is the solid line. Okay, notice that here there is also this dashed line that is superimposed with the solid in this region, in the BCS regime, but then in the deep BC is completely different. So, and the dashed line is only mean field plus renormalized group of the superfluidity, and the solid one instead contains also Gaussian fluctuations. So you see, Gaussian fluctuations are important because they are diminishing the Berezinski-Kosterlitz-Towles typical critical temperature. There is a discrepancy between theory and experimental data. Well, okay, there are several reasons. We did the numerical calculations in the uniform case. Instead, the experiment is in an harmonic trap. Moreover, maybe the experimental data are also affected by 3D effects. Instead, our calculations are truly fully 2D. Okay, to conclude, I have shown that after regularization, and if you want a comprehensive review of method of dimensional regularization for ultra-cold atoms can be found in this review. Beyond mean-field Gaussian fluctuation give remarkable effects for superfluid fermions in the BCS-BIS crossover, 2D BCS-B crossover at 0 temperature. The logarithmic behavior of the equation of state, that is the Popov equation of state, would agreement with the quasi-0 temperature experimental data. Also at finite temperature, beyond mean-field effects, with the inclusion of quantized vortices-antivortices become relevant in the strong coupling regime of the crossover. And what is important, and that the fact that the superfluid density is renormalized, and obviously this changes a lot the Brzezinski-Kosterlitz critical temperature, in particular in the BC regime. Thank you very much for your attention.
Thank you.